Oh yeah. So I'm supposed to be Spock. Oh, thank you. Can you turn me on? Okay. How's that sound? So I'm supposed to be Spock, and my daughter this morning mistook me for Shrek, because she always gets those two confused. So I said, no, I'm Spock. I guess maybe we both have green blood or something. But anyway, this is a bit of actually chapter 6 and 7 concept. Remember that for collisions, the reason that impulse is negligible is because during a collision, the forces, I guess during the collision, it's a very small amount of time for which the collision is happening. So if you want to just analyze what the situation was right before the collision to right after the collision, it might be like a thousandth of a second. And during that small delta t, there's not much ability for an impulse to come from external forces. So, and that's the same not just with collisions but also with explosions. And so here we are analyzing a firecracker, and the situation that we're comparing is the original firecracker just before the explosion to the firecracker right after the explosion. So the two statements are the total momentum of the fragments immediately after the explosion is equal to the original momentum of the firecracker immediately before. And statement 2 is that the total kinetic energy of those fragments immediately after the explosion is equal to the original kinetic energy of the firecracker if it's moving. Have a think about that. I'll give you 1 minute to discuss. Okay. Is everybody able to click in on that? Anybody need more time? 5, 4, 3, 2, 1. Something's not wrong, not going well here. Are people able to answer? I'm having a glitch out here. Couldn't connect, refresh it. There we go. Okay, it should be showing now. So, yes, the idea here is that because it's a very small impulse from outside forces such as gravity, which is the only way you can change momentum is with an external force, that impulse is 0, so the momentum is equal. So that's true. But the kinetic energy is not conserved, and that is because, I'll just write it out here, so the answer is just statement 1 only. Chemical potential energy is transformed into kinetic. That's what an explosion is. So I guess there is some sort of conservation of energy, but there's a transformation from chemical to kinetic. Questions on that? You good? Should be plenty of seats. You can just beat your way through the row there. So today, what I'd like to do is finish up chapter 7. So test, the midterm 2, second midterm test will be on chapters 5, 6, and 7. So this, once we're done today, that's sort of all the testable material. The room that you're going to go to on Tuesday, November the 13th, is actually based on the first few letters of your last name. So A through L-O-C-H goes to EX200, and L-O-K-E, I guess to the end of the alphabet, it goes to EX100 downstairs. And this has gone off the bottom of the page, but basically if you have a course conflict, you can write at the alternate sitting, which is earlier, but it's in a different room that she will email you. And also, what fell off the bottom is that if you already registered for the first midterm alternate sitting, you don't have to re-register. You're going to automatically be put in the alternate sitting because we'll assume you have the same conflict for the second midterm. So actually, if you wrote the alternate sitting for midterm 1 and you want to write the regular sitting for midterm 2, then you should tell us. Otherwise, you don't have to do something. I've actually, almost every day that I do these learning catalytics, someone complains that the textbook falls apart when you open it up, and it's all the loose leaf pages are scattered all over my dorm room floor and stuff. And so this is, you know, this is time to get organized, you know. Be the boss of those pieces of paper. You being the human, higher up the food chain. Get them together. And I think actually what's good is that if you know we're working on chapter 8, get a duo tank for chapter 8 and you can take it with you in the subway and it's lighter than... Anyway. Oh, there is this mysterious thing which you may have noticed on your Quarkus gradebook called LC Hour 19, LC Hour 20, LC Hour 21. There's these items which seem to be marks out of 4 or 5. So that's actually these learning catalytics questions. You can find this information over on the, I guess the Mastering Physics gradebook, but the problem with that I don't like is that half of your marks are 0 over there because of this weird software glitch. So I just fixed it and with Excel and put it on Quarkus. So anyway, that's what that's all about. You don't have to worry about it. I'm going to go on. So today's material, once again, we're finishing up chapter 7. I'm going to start with 7.8 on power and then finish with 7.9 on gravitational energy in space, I guess. Are we good? Yeah, so power. Power is, again, one of those words which has a meaning in English with all these definitions in the dictionary, but in physics it has a very specific meaning. Again, if anybody has any questions, just let me know. Just tell me. So in physics, there's an equation for it, which is it's the work done, or the change in energy of something, divided by the time that it took to do that work. So for example, this woman started off with maybe 0 velocity and 0 height if you define y equals 0 as we're at the bottom of the stairs. But if she runs up the stairs and ends up with some final velocity and final height, she has done work on herself. And it's been done in a certain amount of time, so there's a certain amount of power involved with that. And so it's easy units. Units of work is joules. And the units of time in SI is just seconds, so it's joules per second. So can anyone tell me what the unit is for power? What's it called? Yes? What? What? All right, okay. I'm just messing with you. Okay, and so 1 joule per second is watt, and if you have 1,000 watts, it's a kilowatt. And so you hear about kilowatts a lot. Yeah. So. Rita raises a package, a 10 kilogram package at a constant speed to a height of 2.5 meters in 2 seconds. I think the assumption is she starts at 0 height and raises it up. If she were to raise the same package to the same height in 1 second rather than 2 seconds, how would the work change and how would the power change? I'm thinking something seems more when you do it faster, but let's see what you think. Think about that and click in and then you can discuss. Okay. Survey says stop. Okay. Yeah, so what I think there is that in both cases, the work done is equal to, just look at my notes here. So power is equal to the work done divided by delta T. In both cases, the work done here is sort of the change in energy, which I think will be UG final minus UG initial or something. Okay, so it's going to be the same in both cases. You raise the box by the same amount of height. And there isn't any mention of kinetic energy change. But the power doubles if the delta T is half. Make sense? Any questions about that one? Do another? Hopefully this is showing up for you. I'm having strange connection problems on my computer. You can see it? Okay, so this one is about a sports car, and this one's a little more difficult. So I read about this, I don't know, it's a Maserati or something, that it could go 0 to 30 in 1.5 seconds. And it was an American website, so it was 30 miles per hour. But anyway, I want to compare that. And so 1.5 seconds is sort of the delta T, I guess. How long should it take to go from 0 to 60? Twice as fast as your final velocity. So what's happening? Your engine is providing some amount of power to change your, I guess, your energy, your kinetic energy, right? So, and the assumptions I'd like you to make just for this very rough order of magnitude estimate are, number one, that the power is constant. Like the maximum power, you floored it, so that's the maximum power you can get out of your engine, and that doesn't change as velocity increases, so that's probably not great. Power of engine is independent of velocity, and secondly, I'd like you to neglect friction and air resistance, which also probably isn't great, but I think what this means is that all the energy is just going into kinetic energy. I'll let you think about that for a minute, see how you do. I'm going to stop it, and then we're going to discuss it. Ready? Final answers? So it's like it says sort of B or D, but I think it's D. So, and this is how I got it. Power is constant, and I'm going to say that the delta E is going to be the kinetic final minus 0 in both cases. So let's just start with maybe the 30 miles an hour, and then, so this is, I guess, V final 1, and this one is V final 2, which is equal to 2 times V final 1. So what you've done here is you've doubled that final speed. And now I want to know something about the delta T, how that works out. So delta E is going to be 1/2 mv final squared minus 0. So if you double V final, then I guess delta E2 is equal to, I guess, 4 times delta E1. Okay. So V final squared goes up by 4. Mass doesn't change, and the half doesn't change, but does that make sense? And so since the power is equal to delta E divided by delta T, then you can solve that out. So delta T is equal to delta E divided by the power. And if the power is the same in both cases, then delta T2 is equal to 4 times delta T1. And so then it's a matter of multiplying 4 times 1.5. And I had to do that on my calculator because I'm so bad at math, but I think it's 6. My wife makes fun of me because I pull out my calculator for the most easiest algebra things, or arithmetic things. I'm pretty good at algebra and calculus, but I'm really bad at arithmetic. It's just, I don't know why. It's 6. Any questions about that one? It was a hard one. In order to get to 60 miles an hour, as opposed to 30 miles an hour, you need to double your speed, so you need to have 4 times as much energy. So it's going to take 4 times longer, assuming that your engine delivers power at a steady rate. Okay? Okay. I think that might be it. Well, okay, so the other thing I wanted to do, since we're on the subject of power, and you hear a lot about watts, is tell you about electric power. So here in this province, the company that sells you electricity, that's running everything here, is called Ontario Hydro. And they charge you per kilowatt hour, which is a bit strange. A kWh, or a kilowatt hour, is the amount of energy used by a power of kilowatts, 1 kilowatts times 1 hour. So you do 1,000 joules per second and you multiply it times an hour of time, and you end up with, it's actually 3.6 million joules. So how much do you think that you would pay for 3.6 million joules? I might pay a lot. I don't know, it seems like a lot of joules. But turns out a joule is very, very small. It's, I guess, 1 Newton of force pushed on something for 1 meter, right? And it turns out to be very small. So you get it for about 10 cents. But it's actually not that easy. They have in Ontario something called time of use pricing. So I want to explain that to you. So, the reason it's called Ontario Hydro is because back in the old days, most of the electricity used to come from waterfalls, like Niagara Falls. Niagara Falls goes down, it turns some turbines, and that generates a lot of electricity. And there's other waterfalls around Ontario and dams where the water is going through and that water is generating electricity. These days, most of our electricity, 63% of it actually comes from nuclear power plants, and 26% still comes from actual hydroelectric. Every year, they increase the amount of wind farms in the province. There are now up to 6% of our energy is coming from wind. And then fossil fuels makes up sort of the remaining 4% of our energy. And you can certainly turn on or off the gas plants, but these other sources of like nuclear power, you can't really just turn off your nuclear generator. It's going, and certainly you can't turn off Niagara Falls, so they're going 24/7. But humans use energy on sort of a schedule, a weekly and daily schedule. So I think Ontario Hydro has to store the energy in batteries somehow and then give it back to us. I think that's the reason that they say this on their website. By adjusting your usage habits, TOU pricing enables you to save money during hours when electricity is more expensive. So they want us to adjust our daily lives. So for example, in the summer, everyone's air conditioner comes on sort of between 12 and 5 when it gets really hot outside. And so they make it the most expensive time to buy electricity, but not on the weekends for some reason. In the winter, I guess everyone is turning on their toasters and things in the morning to make their breakfast, and then they kind of leave the house, and then when they come home, they're making dinner, and so those are the peak times, and they want us to try to avoid those times to turn on the dryer as well. And so if we spread out our usage a bit, then it helps Ontario Hydro deliver power more efficiently. So now I want to do a little example of this, and this will give you some practice at swapping around on these units. Especially kilowatt hours are a bit strange to use, and they will turn up on the midterm. So. Your clothes dryer uses 5,000 watts. So I just looked that up in the manual for my dryer. It's pretty typical. And let's say you need to run it for 1 hour to dry your clothes. So the power here is 5,000 watts. So this is equal to 5 kilowatts. Okay. And one load is equal, it takes 1 hour of time, I guess. So this is, your delta T is 1 hour. If you run in an on-peak time, such as between 7 and 11 on a weekday, the cost is, this rate, I guess, that you have to pay is, on peak, is 13.2 cents per kilowatt hour, which is that's you have to figure out how much energy you're using. And then the rate, if you were to do it on the weekend, would be 6.5 cents per kilowatt hour. And the question is, how much money can you save per load by doing your laundry on the weekend as opposed to during an on-peak time? And if you do 50 loads, how much do you save? So I think the way I could do it here is I could sort of convert across. There's not really a diagram for this, so I've skipped a couple of steps, but the cost is going to be something like the rate times delta E, okay, which is rate times P times delta T. So what you've got is, let's do the cost for the on-peak. That would be your 13.2, and we should put the units here because otherwise we're going to get confused, cents per kilowatt hour, times the power, which is 5 kilowatts, times the hours, which is 1 hour. So the way the units work out there is the kilowatts times hours cancels the kilowatt hours, and you just get 13.2 multiplied times 5. So this is 66, and the only things left is cents. And then the cost for the off period is going to be similarly 6.5 times 5 times 1. That's going to be 32.5 cents. So the savings is what you would have paid if you'd done it on the on-peak minus what you pay for the off-peak, and I got 33.5 cents, which doesn't seem like much, but if you do 50 loads, then your savings is 50 times this. 50 times 33.5, which is, I got 1675. So that's actually $16.75 if you do 50 loads of laundry in a semester. And I think that's all I have to say about 7.8. Next we're on to gravity. Seems unrelated, but it's also about energy. Okay. So the first thing I'm going to do with gravity is try to remind you of the real equation for force of gravity. So if you have force of gravity on this ball, does anyone know what the equation is for force of gravity? You find F sub g for this. If the mass is m. Any thoughts on that? mg. Right, so mg. But then there's this other equation, which I think we said is going to be equivalent, which is this one. So mg is correct if you're near the surface of the Earth, but what Isaac Newton realized is that there's this universal force of gravity in which any two masses, m1 and m2, are attracted to one another by this force, g m1 times m2 divided by r2 squared, where r2 is the distance between the centers of these two masses, and they get attracted towards each other. So what the heck does that have to do with mg? What it has to do is that this ball, it is attracted to like that speaker over there and me and, I don't know, the clock and everything, but all of those are negligible compared to the iron core of this big Earth, which is 6,000 kilometers downwards and weighs 6 times 10 to the 24 kilograms or something. So if you set m1 to be the mass of the Earth and r to be the distance from the center of the tennis ball to the center of the Earth, you get 9.8. So capital G times mass of the Earth divided by radius of the Earth squared equals 9.8. So 9.8 times whatever the mass of the tennis ball is, and that's where the mg comes from. And over capital G is this crazy 10 to the minus 11 thing. So what about this equation? This is gravitational potential energy. It's in your 7.9 chapter. Can anybody see what the differences are? What's the difference between this previous slide? It looks exactly the same. Anybody see any differences? Before? So force, energy. What's the difference? Yes?
The radius of the square.
Yeah.
And also negative.
Also what?
It's negative.
In the negative. So absolutely fantastic. So there's the first one, I think the most important one is that the radius isn't squared for the energy because it's a different unit. It sort of makes sense, right? This one is in newtons and this one's in joules. Hey, and you've even got, for work is force times distance, right? So you kind of would expect the r squared to go to an r to make the units all work. Anyways, and the other one is the negative sign. The negative sign is a very mysterious thing, and I'm going to go over a little bit. Okay, so you have to believe me that somehow this is the same as mgy, which was our old equation. In the same way that I'm telling you this is the same as F equals mg for force of gravity. So this is the real equation, and the approximate equation is mgy. So we've chosen here the 0 point of potential energy to be at r equals infinity, where the masses will have no tendency or potential to move together. If they have no potential to speed up, because it's too far away from each other, they have no potential energy. Sort of makes sense, right? And then don't forget that the r is the distance between the centers of these two things. So why is it 0? Why is it negative? That's my big question. Gravitational potential energy is 0 when the objects are at an infinite distance apart. The only way to add positive energy to a system, so if you take this ball, for example, and you push it away from the Earth, you're increasing the distance between the center of the ball and the center of the Earth. So you're increasing r, and you're adding energy to the system. So if you pull these masses apart from each other, you're adding energy to the system. And the only way to add energy to a system and then at the end have it become 0 is if it started off being negative. Let me just say that again, but in terms of this energy bar graph. So what they're saying is that in order to increase r out to infinity, you have to do this work, positive work. And then when they get out to infinity, they end up with 0 energy. So something plus this positive thing equals 0. So the original thing had to be negative. That's why they put the minus sign there. But the basic idea is that if you want to get back to an object that is sitting on Earth, then you just set m2 equals the mass of that object, m1 is the mass of the Earth, and r is the radius of the Earth, because that's about the distance from the object to the center of m1, right? So this equation just becomes this GME. I'm not sure where the y gets up on the top, though, but you can check it. Oh, well, let's do this. Let's do a concept question first, because this is an important concept. Probably should say configuration A and configuration B, but anyway, A is configuration 1, B is configuration 2. It's the same two planets, but they're at a different distance. Which of these two configurations has more gravitational potential energy? So give you a minute on that. Definition of more. Let's think of it this way. If one student has an OSAP debt of $500 and the other student has an OSAP debt of $10,000, who has more money? More. Who's like richer, I guess. The reason I'm talking about debt is because the question is, they're negative. It's the negative, remember that negative? GM over R. You got it further, but anyway, that's my hint. Yeah, so indeed, the idea here is it's configuration 2. And actually, the way that I look at this, I'm hearing the shushing from the other room there, is that these guys, or maybe planet B or something, it has more potential to fall. Can you picture that? What is potential energy, after all? It is the potential to move. Something that has potential energy that gets coiled up spring contains potential energy. It means if I pull this stick, then something's going to move, meaning the ball's going to move. Okay? And similarly, this planet is going to fall towards planet A. And this planet's going to fall towards planet A. This one's got further to fall. It's going to get there going faster. It's got more energy stored in it. And the other way of looking at it is that that thing about the debt thing. This R is greater, so that means that the GMM over R is less. So this is less negative than this. Make sense? Less negative is more. Because it's up higher, closer on the number line to 0. Nobody told you it was going to be easy, right? Okay, so here's another question. How could two equations that look so different be the same? You might have convinced me with the mg being the same as the gmm over r squared, kind of. But one's negative and one's positive, and that gets a little fishy for me. But we could try it with an example. Let's take our cat to eat a dessert at the CN Tower restaurant. I don't know why anyone would do that. Maybe just tuna. And we can do it one of two ways. 5-kilogram cat starts at the bottom of the CN Tower, where y equals 0, goes to the restaurant, y equals 350 meters. We can use good old mg times y. We're going to have to subtract mgy2 minus mgy1. Final minus initial, right? And so you get 350 minus the 0, 17,000 joules. So we're going to try to do that same calculation now, see if we get the same 17,000 joules, but we're going to use this crazy equation instead. It doesn't look good to me, especially because of that negative sign, but we can try it. Okay, so this is the tricky part. R1 is now the distance of the cat from the center of the Earth at the bottom of the CN Tower, and R2 is the distance of the cat when he gets to the top of the CN Tower. So this is where significant figures start to get a little strange. I just was only able to find this on Google out to about this number of meters. So I just assumed there was a bunch of zeros after it, even though there probably aren't. But only the difference is probably going to matter much, so I just added 350. So I'm saying, let's just say the cat started at 6,371,000 meters exactly from the center of the Earth, and then he went up to the CN Tower, and now he's 6,371,350 meters away from the center of the Earth. You with me? I'm not sure those numbers are exact, but the difference is exact, and that's what counts. So now I'm going to do minus GMM over R minus GMM over R1, R2 minus R1. So that flipperoos the R1 and the R2s. And then R1 was less than R2, and it came out positive on my calculator. And I got 17,000, so it all worked out beautifully in the end. So this actually works. You can check it. So what happened? So I know you're blown away by this. Mind blown? The equations are not quite the same because the 0 points are different. MGY, the 0 is at the surface of the Earth, whereas with this GMM over R, the 0 is at infinity. But since the 0 point's arbitrary anyways, it's the same physical, it's only the delta U matters physically, so it physically describes the same thing. 550. My clock there is a little fast. Okay. Last thing is about escape speed. So, I would like you to imagine a rail gun. This is a schematic design for rail guns. Basically just two pieces of metal. You hook it up to a DC battery, high voltage, and you stick a magnet in between it that connects a circuit, and that thing just goes flying right out of there at high speed. Anyway, it doesn't matter. It's a way of shooting something fast. So we're going to shoot something up, and I'm going to ask, what is the minimum speed a spacecraft must be launched at from Earth's surface in order to escape Earth's gravity? So if I launch this with some initial energy, it goes up to this height, and then it stops and comes back down. And if I throw it really fast, it hits the ceiling and comes back down. But you can imagine, you throw it fast enough, it just is never going to come down. And so I'm going to do that by saying, in order to get to R gets to zero, sorry, R gets to infinity and stop there. Okay, so there's this city that way called infinity. And when you get there, you stop. Okay? And the way you get there, you just keep going. Okay, so I don't know, but do you follow that? When you get to infinity, you can stop. So the energy is going to be, whoops, that's the answer. So let's go to, I want to show you how I did it, if I have enough time. Yeah, I do. I've got plenty of time. I showed you a quick flash of the answer. But basic idea. What is the minimum speed a spacecraft must be launched at from Earth's surface in order to get out to infinity and then stop there? So initially, it starts on the Earth with some V initial, okay, going up. And R initial is equal to the radius of the Earth. Okay, the distance from your rocket to the center of the Earth. And then finally, the situation is that your rocket is out here at infinity, where V final is equal to 0. And now the distance from the center of the Earth is R final is equal to infinity. And this diagram is not to scale. Just imagine it's infinite. So the diagram step looks like this. The K initial is high, and then plus the UG initial is low. You add them up, and you get 0. This is the stop part. So I would just say 1/2 mv initial squared plus negative g times the mass of the Earth times mass divided by our initial with no squared on it is equal to 0. Hey, the mass is canceled. I always have a little, I always say yay when the mass is canceled, so I don't need to know. And then you get vi squared, kind of simplified around, times both sides by 2. The minus goes away because you plus it on the other side. You get 2 times capital G times the mass of the Earth divided by the radius of the Earth. Because don't forget, it started at that distance. And then you just solve it out. V initial is the square root of 2G mass of the Earth divided by RE. You have to look up these constants in that cover of your textbook. Front cover, which is 2 times gravity constant is 6.67 times 10 to the minus 11, and they put it in SI units for you. Mass of the Earth is 5.97 times 10 to the 24, and divided by radius of the Earth is 6.38, according to my textbook, times 10 to the 6. And when I times it all out, I got 11,000 SI units, meters per second. So actually that's 11 kilometers per second. Okay, so that's very, very fast. And we're going to show the answer on PowerPoint, so don't worry. And I'll also scan this as soon as I'm done here. Maybe after I finish trick-or-treating, I'll scan it. Because I'm definitely going. That's the escape speed. And it's 11 kilometers per second. So just letting you know, if you drive your car at 11 kilometers per second, it will instantly get vaporized and explode and be nothing but plasma. So that's because of air resistance. So that's not good. So air kind of messes you up. You can't throw the ball and have it go to infinity. Also note that the mass is canceled, so escape speed does not depend on the mass of the escaping object. It's the same for a big boulder as it is for, say, a helium atom that may be flying around. Helium atoms do go out to infinity because they go fast. They go that fast. I have one learning catalytics question for you. So I think I have enough time. I have 4 minutes, I think. So now what I want to do is think, instead of the Earth, I want to think of two different planets. Planet A and the escape velocity from planet A versus some different planet B and the escape velocity from planet B. We know that planet A has twice the mass of planet B. So from this information, can you say that A, the escape speed must be twice as great for planet A as for planet B? B, the escape speed for planet A must be 4 times as great as the escape speed from planet B. C, the escape speed is the same as for planet B. D, the escape speed for planet A is greater than the escape speed from planet B, but we cannot say how much greater. Or E, we cannot conclude anything about the escape speed for planet A without knowing the radii of the two planets. Cut you off in the interest of time. I'm not going to press stop on the thing. But basically, little m is the mass of the planet. Little r is the radius of the planet. So it is important, I think, to know what the radii of those two planets are. So finishing up, if you guys could just be calm for 2 minutes, we'll get through this, and then we'll say our goodbyes and say Happy Halloween. Ready? Thank you. So this equation suggests something interesting. If the mass of the Earth was either a bunch larger or the radius was a lot smaller, then you would increase the escape speed to beyond 11 kilometers per second. And in fact, you can even get it down, I think if the mass of the Earth was down to a radius, all packed into within a radius of the tennis ball, like a few centimeters, then the escape speed, if you plug it into there, you'd get 300,000 kilometers per second, which is an important number because in physics, you can't go faster than 300,000 kilometers per second. It's the speed of light. So nothing could escape Earth if it was that small. It would be a black hole. And there are lots of black holes in space. We've discovered some of them. One of them is called Sagittarius A star. It's called a supermassive black hole because it has a mass of 4 million times that of the sun. And it's all packed within Mercury's size of Mercury's orbit, right around here, sort of on the border between Sagittarius and Scorpius, sort of in a fall constellation. It's very cool. I got one more slide. I want to tell you that next week is reading week, and there are no classes in arts and science, which means that, even though we just met, it seems, it's going to be a temporary farewell. I'll see you in a little more than a week. Here's some leaves to jump into. And don't forget, there's a test the day after you come back.